Hi everyone. In this lecture, we are going to discuss bitwise operators in Java. Before starts today's session, let us try to recall what have we discussed in our lecture 21. What is compound relational condition? What is the return type of logical operators? Types of logical operators? Principles of logical operators. If you haven't watched that, please watch that. The link is given in the description box. After watching this video, you will get the knowledge about what type of the operations will be done with bitwise operators, principles of bitwise and or and exclusive or, three types of the shift operators we are going to discuss, twist in bitwise complement, difference between right shift operator and unsigned right shift operator. This is the complete picture of the operators of Java. We covered arithmetic operators in lecture 18. After that, we discussed relational operators in lecture 19. In lecture 20, we covered assignment operators with example programs. In lecture 21, we discussed clearly about logical operators. In this lecture, we are going to cover bitwise operators. Bitwise operators are used to perform bit level operations. These bit level operations are also called low level operations. Java bitwise operators are used to work with individual bits of the given value. As these are works at bit level, these are called bitwise operators. These bitwise operators can work with binary values directly and can work with integers also. When you take the values in the form of the integers, internally the integer values will be converted into binary formats, that is zeros and ones, and then on those zeros and ones the bitwise operators work. After implementing bitwise operators, the result is generated internally. Again, that binary result will be converted into decimal. See this? The points will be clear to you. If you enter the input values in the form of the decimals, first the decimal value will be converted into the binary internally, and the bitwise operators works on these binary values. The result will be generated internally in the form of binary. Next step is the binary value is converted into its equivalent decimal value, and finally this decimal value will be displayed as an output. This is how the internal implementation about the bitwise operator when you are working with decimal values. We have several categories of the bitwise operators in Java. Those are bitwise AND operator, bitwise OR operator, bitwise exclusive OR. The symbols we use to represent these operators are AND symbol. This is bitwise AND operator. Pipe symbol is used to represent bitwise OR. Cap symbol or caret symbol is used to represent bitwise exclusive OR. And bitwise complement operator, bitwise left shift operator, bitwise right shift operator, unsigned right shift operator. The symbols are tilde symbol we use to represent bitwise complement, left shift operator two less than symbols, right shift operator two greater than symbols, unsigned right shift operator, for that we use three greater than symbols. This is the complete list of bitwise operators in Java. Let us discuss these one by one with help of the examples. In this list of bitwise operators, all operators requires two operands. So those are called binary operators, except bitwise complement, which requires only single operand. So bitwise complement operator is a unary operator. Remaining 6 operators are binary operators. Coming to the bitwise AND, the principle of the bitwise AND operator is the output of bitwise AND is 1 if the corresponding bits of two operands is 1. If two input values are 1, the output will be 1. If either bit of an operand is 0, the result of corresponding bit is evaluated to 0. See this table, you will get the idea clearly. So this is one operand value, this is one operand. So X bitwise AND Y. When two input values are 1, the output of bitwise AND becomes 1. See this example. We have two input values 12 and 25. Let us try to find 12 bitwise and 25. As we discussed already, when we are working with decimal values, internally, first the decimal value will be converted into the binary values. So this is the equivalent binary value for the 12, and for the 25, this is the equivalent binary value. Coming to the 12 and 25, apply the formula of the bitwise AND. When two input values are 1, the output becomes 1. In all remaining cases, nothing but you may have 0 and 1 or 1 and 0 or 0 and 0 also. In all the cases, you will get 0 as an output. After converting this binary value into the decimal, the final value is 8, that will be displayed as the result of this one. See this example program to implement bitwise AND. See here, int A assignment 12, B assignment 25. Just I want to print A bitwise AND B. Let us execute this. Now you can observe, as we discussed, the output is 8. One more important point is, the bitwise operators won't work with float values. Suppose, see the 7th statement, I declared two variables A and B of float type. Now I want to find out A bitwise and B. But now you can observe, you will get the error message here. The operator bitwise AND is undefined for the argument type float. So you cannot work with float values when you want to implement bitwise operators. Next category is bitwise R operator. The principle of the bitwise R operator is, the output is 1 if at least one corresponding bit of two operands is 1. Otherwise, in all the remaining cases, bitwise R returns 0. In other terms, we can say that bitwise R returns 0 when the bits in both operands are 0. Otherwise, it returns 1. These two principles are same. See the truth table for the bitwise R. See, when you have two input values, two operand values are 0, the output becomes 0 in all the remaining cases. That means you may have 0 1 or 1 0 or 1 1. The output becomes 1. See this example for the better understanding. I am taking same values 12 and 25 but implementing R operator here. So equivalent values in the binary values. Then we are going to find bitwise R. The rule is, when you have two zeros, the output value becomes 0. See now, same values. We are trying to print A bitwise or B. Let us execute this. Now see 29. So we are getting the same output 29. Bitwise exclusive OR. The principle for the bitwise exclusive OR is, it returns 1 if the corresponding bits of two operands are opposite. In all other cases, it returns 0. See this truth table for the bitwise exclusive OR. In this case, the two values are opposite, 0 and 1. So the result is 1. And this case also opposite values. One operand value is 1, another operand value is 0. So final value is 1. So in all other remaining cases, like two values are 0 or two operand values may be 1. In those cases, the output is 0. Understand about the bitwise exclusive OR with the same values 12, 25 and 12 exclusive OR. Now the principle is, when you have opposite values, observe the green color, 1 0 1 0 1 opposite values, so output is 1. Here also 0 1 opposite values 1. In all other cases, the blue color cases are 0 0 cases, okay, 0 0 zeros, and 1 1 case also 0. So finally 12 bitwise exclusive or 25 value becomes 21 in the decimal value. Let us try to implement this. See this same program, execute it. Now see, the output is 21. Next category is Bitwise Complement operator. This is also called Bitwise NOT operator. As we covered already, this is unary operator, means it requires only one operand. It complements the given value. It changes ones to zeros and zeros to ones. See the truth table. If the input is 0, the output is 1. If the input is 1, output is 0. For example, the input value is 10. The complement 10 value is like this, nothing but 0 become 1. Here also 0 becomes 1, and so on. 1 becomes 0, 0 becomes 1, 1 becomes 0. So the final answer of Bitwise Complement 10 is minus 11. Bitwise Complement x value is equal to minus of x plus 1. In our example, x value is 10. So minus 10 plus 1, that is minus 11. So by using this formula, you can easily calculate the value. But the twist in the Bitwise Complement is, observe carefully, this is the Bitwise Complement value we have taken from this previous slide. This is the Bitwise Complement value, right? So we are taking same value here, and I want to convert it into the decimal value. If we convert this value into the decimal, the value is equal to 245, but the output is minus 11. To get the actual answer of the Bitwise Complement or Bitwise NOT, we need to find out 2's complement of this number. The 2's complement of a number is equal to the complement of that number plus 1. I will explain it with an help of the example. See now, 245, we have taken the same value from the previous slide, okay, 245. Then next step is find the 1's complement. To get the 1's complement, 1 becomes 0s, 0 becomes 1. See now, 1 becomes 0, 0 becomes 1. Then add 1 to this 1's complement value. So we are adding 1, okay, binary addition rules. 0 and 1 is 1, and 1 as it is 1, 0, 0 as it is, and so on. Remaining all are as it is. This value is 2's complement of this 245. Then this 2's complement of 245 will be converted into the decimal value. That decimal value is minus 11. In this way, we are getting minus 11 as the final value of Bitwise Complement. Let me show it practically. See this Bitwise Complement example. A value is 10. Bitwise Complement A. So let us try to observe the output. See, the output is minus 11. I think it's clear. So in the binary number system, one bit is used to indicate sign of the number. In sign bit, 0 indicates the number is a positive, and sign bit 1 indicates that is a negative number. Left shift operator, this is also called signed left shift operator. This is used to shift all bits towards the left by a certain number of specified bits. Simply it is used to move some number of the bits to the left hand side. The bit positions that have been vacated by the left shift operator are filled with 0. See this formula. If you perform left shift operation on any operand, let us say operand is x, with I times I number of the bits, we are trying to move to the left hand side. Then we can write like this: x left shift operator I the final value becomes x into 2 power I. It will be clear in the next slide. For example, we have the value 12 in the variable x. First step is that value will be converted into the binary values. As we are working with bitwise operators, all these operators are used at bit levels. Then the operation is x left shift operator 1. Nothing but all the bits should be moved one cell to the left side. Observe here, this is the given input value. This cell value will be shifted to the left hand side by 1. In the input value, this value in the first cell, but in the generated value, the same value becomes in the second cell because that is moving to the left hand side by 1. In the same way, second cell value store into the third cell. This value comes to here. Every value shifted by one cell to the left hand side. If we implement like this, in the result value, we have an empty spaces and we have an extra space in the given input. So this value will be vacated and this empty space will be filled with zeros. And finally, this value will be converted into the binary value. As per our formula, see now 12 left shift 1. The value is 12 moving to the left hand side by 1 bit. So if we apply this formula, you will get the value by using the formula 12 into 2 power I, where I value is 1, x value is 12. 12 into 2 power 1, 12 into 2, 24. See this same example, input is 12, implementing x left shift 1. Execute it. We are getting 24 as an output. Right shift operator, or you can say signed right shift operator. It shifts all bits towards the right by a certain number of specified bits. The bit positions that have been vacated by the right shift operator are filled with 0. The formula for the right shift operator is x is a operand right shift by I number of the bits. X division operator 2 power I. Very important point is the right shift operator is used to shift the bit towards right and also preserves the sign bit, which is leftmost bit. This is important point. So when you work with right shift operator, preserves the sign bit. So to indicate sign of a given number, the binary number system maintains one bit that is called sign bit. Generally that is leftmost bit. 0 indicates positive number, 1 indicates negative number. So left shift and right shift operators preserves that sign bit. After performing right shift operator on positive number, we get positive value as the result, and if we perform right shift operator on the negative values, we get negative value as a result, because the sign will not be changed. It maintains the same sign. This is very important point. See this example with the same value 12. This is the equivalent value in the binary number system. We are implementing x right shift operator by 1. So observe here. To understand this right shift operation, start the operation from the left hand side. So first bit should be moved to the second cell, moving that value for the right hand side by 1. In the same way, second cell value of the input becomes the third cell value in the x right shift operator 1 result. So you can understand like this, every value shifted to the right side by 1, and this value will be vacated and this empty space will be filled with zeros. So finally the value is 6. 12 right shift operator by 1 as per the formula 12 division 2 power 1, okay, where I value is 1. The answer is 16. See this example. Input value is 12, x right shift 1. Execute it. So the output is 6. Okay. Next one is unsigned. Unsigned redshift operator shifts all the bits towards right by certain number of specified bits, but it stores 0 in the signed bit. So the important point is it stores zeros in signed bit. We covered a very important point in the redshift operator, that is redshift operator preserves the signed bit, but here the unsigned redshift operator stores 0 in the signed bit. Since it fills always zeros in the signed bit, so it is also called zero fill redshift operator. Unsigned redshift operator always fills zeros in the signed bit. That's why it is also called unsigned redshift operator. Observe the difference between redshift operator and unsigned redshift operator. If we apply unsigned redshift operator on positive number, it gives same output as that of redshift operator. But if we apply unsigned redshift operator on negative number, the output will be positive number. The reason is the sign bit is filled with 0. That's why we will get positive number as the output, even though the input value is negative. But coming to the redshift operator, if the input is negative number, the output is also a negative number, because the redshift operator preserves its sign, but unsigned redshift operator doesn't preserve the sign. Very important point. See this example. So here my value is 240, that is positive value, and implementing unsigned redshift operator. Execute it. So we are getting again positive value. Let me change the input value as negative value, minus 240. Now execute the same program. Observe, the output is again positive value. So this is important point about unsigned redshift operator. Check your knowledge, what you learned from this video. What type of the operations will be done with bitwise operators? Principles of bitwise and R and exclusive R. 3 types of these shift operators we covered: left shift, right shift, and unsigned right shift. Twist in the bitwise complement. Difference between right shift and unsigned right shift operators. If this video is useful to you, please subscribe the channel, watch the videos, like and share it. Thank you.